Assalamualaikum warahmatullahi wabarakatuh and hi. So today for week one, we will be discussing a little topic for our subject electrical drivetrain. That is more of a topic that I would consider as a revision. So it's a revision of physics as we mentioned in the briefing class just now. So electrical drive system is quite a huge chunk of system that englobes can be ranging from the power electronics, the energy storage or energy supply, the electrical machine itself, and the transmission towards the application. So the largest part is basically involved in all turn around the utilization of electrical machines. So as I mentioned, the meaning of electrical machines here is basically the electric motors of generators. So in our case, it's going to be motors because we are going to drive a certain application, right? So there will be quite a large focus on electrical machines, on motors. So we need, I think we need a quite some revision in order to be familiarized with some terms that are going to keep on coming back when we discuss about electric machines, electric motors. And these terms are basically related to the construction of the motors, which depends on magnetic circuits and magnetic materials. So this week, to start the subject, I would like to spend quite some time on revising these topics that is mostly physics of probably matrix or high school. I mean, not high school, STPM or matrix. Uh, so let's start with this kind of revision related to magnetic circuits and magnetic materials. Several terms that we need to properly understand and standardize so that as we discuss about electric motors, we all understand the same thing. Okay. So lesson in this lesson are related to magnetic circuit and magnetic materials. We're going to start with the revision of some terms standard in order to standardize the understanding related to the terms magnetic forces, magnetic fields, and Faraday's law. What are they? And then we'll go into introduction of magnetic circuits. So this is going to consume about 1 week, these two alone, and then we'll talk about flux linkage, inductance, and energy. So this is related to the transformation of energy from electrical to electromechanical to motors. And then we'll talk a bit about properties of magnetic materials, and then AC excitation. So AC excitation means the current delivered to the motors in order to rotate the motors. So we need to do some revision on, for example, sinusoidal current, and then sine wave or three-phase current. We'll talk about it a bit, and then at the end a bit on a permanent magnet at the end of the lesson one. So let's start with a revision on magnetic field and magnetic forces. So we need to understand this term properly. What is magnetic field and what is magnetic forces? So the thing that we observe first is basically magnetic force. The thing that we can feel, and when you, for example, when you displace a certain ferromagnetic material, let's say a pins or a nails close to a permanent magnet, the thing that you are experiencing and feeling on your hand, in your hand, is basically a force, right? So that's what we call magnetic force. So the question would be, what is a magnetic field then? So magnetic field is basically it arises from permanent magnets and electric charges in motion, but it is not an object that you can observe or you can touch. It is basically a tools that mathematician creates to describe an area. So a field is basically like an area in which there will be magnetic force if there is an object interacting with that magnetic field. So let me explain. So magnetic fields basically are the result of motion of charges. So imagine, let's look at these conductors. If there are electrical current, therefore charges circulating in here, what happens is around it there is a certain area, what we call field, where if you place anything that interact with that magnetic field, you can feel the force. So it is not something that is visible. It is not something that you can feel. What you feel is not the field. What you feel is not the field. What you feel is basically the force, because the object that you are touching is placed inside the field. So the field is basically can be so magnetic force is the force experienced by an object placed inside that magnetic field. So an object like a permanent magnet or conducting current will create a field around it. So a field around it. When you place a certain object that can interact with that field, you can feel the force, right? So here basically what we have, what happened in this figure over here is a visualization of that field through what we call field lines with iron filings. So I think you are pretty familiar with this kind of experiment where you put permanent magnets underneath a piece of paper, and then you put iron filings, a powder of iron filings on it, and you see several lines. So this line is describing what we call magnetic field, right? So the more lines, the more intense the line, or more lines in the surface area, it means the magnetic field is higher. When there are less and less lines, it means the magnetic field is weaker. So magnetic force, when you place around an element that creates magnetic field, magnetic force is more intense when you are closer to its source. So when you're closer to a pole of magnet, it's very, very intense. The field is very important. But if as you get further and farther from the element, the source of that magnetic field, you'll feel less and less forces, right? So there is a video in a video that explaining the difference of the terms between magnetic field and magnetic force that I invite you to watch. You can watch it in basically in the link inside the slide that I put in the Google Classroom. So the next term is we talk about magnetic field. So how does we measure magnetic field? So magnetic field is very important because without magnetic field, you will not be able to rotate your electrical machines. The question now is, how do we measure them? So magnetic field is like a field. So it's a mathematical object, a field. It is an area where you describe a certain strength and direction. So it is something like when you see this rotating electrical machine, rotating rotor following a rotating magnetic field on the stator. This line basically describes the intensity of the color, describe the intensity of magnetic field, and the arrows that you see is describing the direction of magnetic field, right? Okay, so how do we measure it? So this description of imagine if you want to measure a magnetic field, measuring the what we call the direction of magnetic field is easy. For example, if you have a compass, so a small magnetic material is sensitive towards magnetic field, and you float it, you can see that it will move so that it becomes parallel towards the direction of the magnetic field, right? So that's easy. But measuring the strength is more difficult and a bit more complex. So for example, the early what we call measurement instrumentation of magnetic field, we call it as magnetometers. The early magnetometers, for example, it measures the intensity of the magnetic field by measuring the oscillations of the magnet inside the magnetic field. So for example, in this case, if you put a magnet like this and you try to deviate it from its usual direction, and it will go back to its steady direction, but it will oscillate, right? So if it's oscillate faster, I mean the oscillation, the frequency is higher, it means that the magnetic field is stronger. But if it oscillates slowly, it goes towards the normal line, the steady state line, slower with a less frequency, it means the magnetic field is weaker. That's how they used to do it long time ago. But now what happened is we do measurement of the strength of a magnetic field using what we call giant magnetoresistance, GMR. So what is giant magnetoresistance? Giant magnetoresistance is basically a properties of certain material which is composed by thin film alternating between ferromagnetic material and non-magnetic materials. So this kind of material, basically what happened is GMR describe the variation of that material electrical resistance when it is subjected to a magnetic field. So there is this kind of material where you have layers of magnetic and non-magnetic material. If you put magnetic field onto it, there will be variation of electrical resistance, right? So you measure the resistance of that GMR. if the variation of that resistance of that material JMR will describe basically the strength of the magnetic field. So basically this JMR properties is the same thing that is being used in your hard drive, in your mechanical hard drive. Of course, nowadays you all are using and converting into SSD, but this hard drive will use the same JMR material. So basically the discovery of that JMR won the discoverer, two person, Albert Fert and Peter Grunberg, a Nobel Prize in Physics in 2007. So that's an interesting point to share with you. So this is the figure of an old magnetometers, right? And here underneath here basically is a finite element analysis of an electrical machine, electric motors. So this is basically a synchronous motor with internal permanent magnet. So you have the scale over here, color of intensity or strength of magnetic field. So purple describe the highest intensity, and turquoise or blue describe a lower magnetic field, right? So basically what is the symbol and unit in which they are measured? The symbol is B, magnetic field B, and the unit, SI unit to measure it is, we call it as Tesla. So what is described by 1 Tesla? What is defined by 1 Tesla? 1 Tesla basically define a force that need to be applied to a moving charge due to the magnetic field, right? So 1 Tesla is basically equals to a force to move a charge inside a magnetic field. So a higher Tesla means a higher magnetic field, so a lot of force that you need to move that charge inside the magnetic field. A lower Tesla means it is easier to move, so less force to move an object, here in this case a charge basically, inside that magnetic field. So just for example, your fridge magnet that you put on your fridge is its magnetic field, or what we call flux density. In other words, we'll talk about that terms, but for the moment a magnetic field that's created by your permanent magnet on the fridge is in the order of 1 millitesla, so it's very, very small. And the earth magnetic field is of course far smaller, is at 510 to the power minus 5 Tesla. And in comparison, a higher magnetic field, an MRI machine, for example, it is at 1.5 Tesla. That's very, very high. So for example, in this machine, you cannot see the figure over here, but the maximum magnetic field in purple over here is basically around at 1 Tesla. It's only at 1 Tesla. So 1 Tesla is already very, very high. It managed to rotate a machine with a certain amount of consequent torque and power. So we talk about magnetic field. So magnetic field is an area described by a certain vector and strength that represent, if you put an object that is ferromagnetic, it means you will feel a certain force. Now let's talk about the origin of magnetic field. So in order to create that magnetic field, I've mentioned just now, you need to have a moving charge, right? So if you have more charge that is put in a higher intensity of motion, you create a stronger magnetic field. So in order to put these charges, let's imagine you have a certain amount of charge. If you want to put this charge into motion, you have two options. The first one is to, not two options, there is two ways in nature that it happens. The first one is a flowing current. We know that a flowing current inside a conductor. So here is the example of a conductor where a current flows in it. Basically, current flows is basically describing a moving charges inside a conductor, right? So if you have a current flow through a conductor, that is what we call an electromagnet, where you create around it a certain magnetic field. There is magnetic field around it. You create magnetic field around it. The magnetic field increase if we observe it. What happens is if you take a certain object that can interact with the magnetic field, so that you can feel the magnetic force, right? So if you go closer to the source of current, if you go closer, then you find out that the force is more important. So it is proportional to the distance. The closer it is to it is inversely proportional to the distance with the conductor. And in terms of current, the higher the current, the more intense the magnetic field. So this relation is described by this Ampere's law. Basically, it is proportional with current. If you have higher current, you have higher magnetic field. If you are closer to the, so R is basically the distance from the distance from the conductor carrying the current. If the distance is smaller, means you are closer to the conductor, it means you have a higher magnetic field. So there is a certain constant to it, mu zero. 2 pi is because the magnetic field around a conductor like this is basically it is a circular magnetic field around it. And then mu zero is basically what we call the permeability of space or permeability of air. Permeability of air is more or less equal to the permeability of space. Permeability basically describes how good is a medium in conducting magnetic field, right? So for example, a space or air is not a very good conductor of magnetic field. So that's one way. If you circulate a current inside a conductor, you will create magnetic field around it. And the law that describes the relationship between magnetic field and the parameters of the current and the position that you are situated in with regard to the conductor is described by Ampere's law. And then secondly, what you can do is basically we can look at electrons in materials. So if you look at microscopic level, of course, or atomic level, a certain material, a chunk of material are built of atoms, and they have electrons, and the electrons are also moving charges around its proton and neutron, right? So an electron is basically have negative charges, and they keep on moving around the nuclei. In a material where free electron so in a material, basically they have a lot of atoms, and they have a moving electron. If these moving electrons are oriented in the same direction, then you will create the magnetic poles, just like so it's basically described how a permanent magnet is created. So there is a link that is very interesting, explaining how permanent magnet becomes magnetic. I mean, how a material can become a permanent magnet. It has relations with law of general relativity that I don't have a capability to explain it. There is an interesting video for you to go out to check out if you are interested in, you know, just for your curiosity. So these materials that can be transformed into permanent magnet, like the one that you put on your fridge, is what we call a ferromagnetic material. So this material, for example, we have ferrite, ceramic, rare earth material like samarium, cobalt, and neodymium, iron boron. So these materials are usually found as permanent magnet in the market, right? And they are used in electric motors. So the permanently magnetized material is called permanent magnet, and they are basically one caveat is that they are sensitive towards temperature, because heating, what happens when you heat a material, the structural the atom will keep on moving, and they are vibrating, and it can rearrange the microscopic structure. If they are rearranged and not oriented in the same direction, then the magnetic field will cancel each other, and it becomes non-magnetic, right? So a permanent magnet, you cannot heat it up until a certain level of temperature, or else you will demagnetize it. So that's the origin of magnetic field. We discussed now there is something that is interesting that we talked about just now about magnetic force. So magnetic force is when you put something, a conductor, for example, inside the magnetic field, you may experience what we call magnetic force, right? So it is a consequence when an object with a moving charges, let's say a conductor, you have a wire where you have current in it, and you place it inside a magnetic field, you will experience a certain force, right? So that's what we call a Lorentz force or magnetic force. This magnetic force is initially quantified for an amount of charge. So it's quantified as current conducting in it. It means quantity of charge conducting in it. So the most not fundamental, the smallest form of Lorentz law is described by a quantity of charge. So it's quantity of charge multiplied by its speed. So a moving current is basically a charge moving with a certain speed inside a conductor, right? Multiply by a cross product, vectorial product the with the magnetic field that is inside will produce a certain force. So this force is can be found basically using what we call the right hand rules. It is a cross product. Cross product means when you a cross product between the speed and the magnetic field will produce another vector in the orthogonal direction. So it means let's see, if you have magnetic field in this direction and current in this direction, it will produce another vector that is perpendicular or that is normal to this both magnetic field in current, orthogonal to it. So you have in this direction of your thumb. Okay, so this is the force. If you have a magnetic field in this direction and you put a conductor that carrying current in this direction, this conductor will basically experience force that pushing it upwards, right? So if we expand the cross product, so without the vector, cross product we know is a sinus theta between the speed vector and the magnetic field vector. You got the force, the amplitude or the strength of force equals to number of charge multiplied by its speed, multiplied by the magnetic field, multiplied by sinus theta. So sinus theta is the angle between the vector current and the vector, the vector speed of the current and the vector of magnetic field. But we know that we usually in electric motors, in a more practical way, we don't talk about charges, we talk only about current. And as we know that current Q over T, current is a quantity of charge per time. So we can describe basically QV as I multiplied by L, because Q, what is Q? Q over, if we divide what is V? V is basically the speed, is basically the length over time, right? The length across which the charges go through per time. So if we replace V equals to L over T, and we know that Q over T is current, so it is more practical to describe it as current multiplied by length. So if you have a length of conductor like this, and you have an intensity of current that circulates as at current I, you multiply that current I with its length, right? And multiply by, so IL is replacing QV, so we have BIL sine theta. I'm sorry, you cannot see theta over here. So the force equals to the intensity of magnetic field multiplied by the current and multiplied by the length of the conductor that is carrying the current, multiplied by the angle between the magnetic field and the current, so that you have the force that is subjected to a conductor carrying current inside magnetic field B. Okay, now that we have defined what is magnetic field, what is magnetic force, and how do we find magnetic force, how do we measure magnetic force and magnetic field, how do we measure magnetic field? Now let's look at another thing, another terms that is very useful in describing the operation of electric motors. We will use this term a lot when we talk and discuss about electrical machines, electric motors, which is magnetic flux. So we'll discuss here about magnetic flux and Faraday's law. So you might heard of Faraday's law. So what is magnetic flux? So magnetic flux again is like magnetic field. It's not something that exists physically where you can touch and you can observe it, but it is a quantity that is very useful to basically quantify the magnetic field in a surface area. So as we said just now, if we have a conducting current, conducting wire conducting currents, we have a magnetic field around it, and the magnetic field is basically it is intense closer to the conductors. As you go further, it's less and less intense, but it covers a certain range of area. But what interests us when we are studying motors, we want to look at only a certain spot of area. If you only want to look at a certain spot of area, what we want to do is we want to quantify the magnetic field inside that particular area. So that's why we call magnetic flux. So magnetic flux is a measurement of total magnetic field on a surface area. So it is the product of B multiplied by A, the surface area that we are interested in, because we only want to look at a certain surface area, and multiply by cosinus theta. So cosinus theta, what it is? It is the the angle between the normal of the surface A. So what we call normal is that if you have this surface, normals mean a vector that is perpendicular to the surface, right? So it is the angle between that normal of surface A and the magnetic field B, right? So it describes the magnetic field on a chosen surface. Only the component of the magnetic field vector, which is normal to our test area, are considered, right? So it means that magnetic flux is maximum when B is perpendicular to A. So it means if your magnetic, let's see this example. If we have a magnetic field that is constant horizontally, vertically like this. If you have a completely flat or horizontal surface A, then you have a maximum magnetic flux. But if it is tilted like this with a certain angle theta, then cosinus theta of course will reduce, because cosinus theta, when it is 0, it is equal to 1, so magnetic flux is BA. But when it is tilted, cosinus theta becomes smaller than 1, so your magnetic flux becomes smaller and smaller. So it means that the intensity of the magnetic field on the surface becomes less and less, because you tilt it, it goes more and more parallel towards the, so the surface experience less and less magnetic field. That's how we can say it in simple words. So imagine if imagine my phone is the surface that we are interested in, and the magnetic field is just like in the figure, going to the bottom vertically. If you have your surface completely parallel with the magnetic field, then your surface will not experience any magnetic field at all, right? So it becomes 0. If it is completely flat and perpendicular towards the perpendicular to the vector of magnetic field B, then you have the maximum. So you can see that all the field line basically tap into the surface. But if you are parallel, no field line tap into the surface at all. So from the formula, we know that it is a dot product, so because it's cos theta, it's not sin theta. A dot product means flux, magnetic flux is a scalar. It's not a vector, it's a certain amount. It represents how much magnetic field do I experience on that surface. The symbol and unit in SI, the symbol is flux, like this, phi, Greek letter phi. And then the unit is in Weber, right? So in relation to magnetic field B is also known as the flux density. So if you look at the equation, imagine if we don't have cos theta, imagine if theta equals to 0, a flat surface. Flux equals to magnetic field multiplied by surface area. So if we isolate magnetic field B equals to flux over A. So flux over A is basically amount of flux per surface area. That's why usually we also call magnetic field as density of flux, or flux density, right? So a higher magnetic field means you have potentially a higher higher magnetic field mean higher flux density when you look at a certain surface area. So the next thing that we want to properly understand is in relation to Faraday's law. So the question that you might ask, okay, now I understand what magnetic flux is. I said that it will be interesting when we studying a motor, but how is it useful? Can you tell me how identifying the amount of magnetic field on a surface area is useful? So this is particularly useful when you study basically electrical machine in the form of a generator. Okay, in the form of a generator, because we know that Faradays have found out the law of Faradays and Lenz's law, or what we may also call a law of induction. So it is the opposite of magnetic force, which means that if you have a wire, a conductor, but this time it is not conducting any current, wire without any current, not conducting current, if you displace or you give force to it, so it's displaced inside a magnetic field, you may produce a certain voltage across the wire. So imagine you have a magnetic field, and then you have a wire that doesn't have any any current right now, and you move it inside a magnetic field. Induction law or Faraday's and Lenz's law said that you will produce a certain potential difference of voltage. So this is called EMF, electromotive force. So I think as you have learned in electrical class, EMF and voltage is the same thing. I mean, yeah. In terms of units or what it is basically potential difference. It's a voltage. You create a voltage when you have the variation of flux observed by the conductor. So EMF or voltage equals to minus d phi over dt. So d phi over dt. It means if a conductor sees a variation of flux, so as we know just now, what is flux? Flux is the amount of magnetic field across an area. If the amount of that magnetic field change, how does it change? For example, you rotate your surface. If you rotate your surface, you change cos theta, so you change flux. If the surface basically see a variation of flux over time, what happens is in that surface you will create a certain voltage. So that is the basic principle of a generator. So a generator, your generator, what happens is there is a turbine rotating a set of coil, and that coil is rotating inside a magnetic field created by probably, for example, a permanent magnet, and it produces a certain voltage, so it supply electricity to the output. So this is described by Faraday's law. Lorentz law is the same thing. Faraday's law, at the beginning they didn't have the minus sign. They didn't indicate the direction of current. And now in Lenz's law it's more specific. They have a direction of current. And in practice, so here is an example over here. I'm sorry, there's my video over here where you cannot see the whole picture. Basically, we have a permanent magnet over here with a certain magnetic field, right? So if you take a cross-section area of this space over here inside the coil, you have a section A. If you push in the permanent magnet, the push in and pull out, what happens is across that surface area, you see variation of flux, right? d phi over dt. So what happens is that you will create voltage inside the coil, and there will be, you can measure a certain voltage, right? But in practice, magnetic induction is created by multiple coils. It's not just one coil, right? It's created by multiple coils. So we add usually an additional terms n may be added to represent the number of turns of coil. So if one coil produces d phi over dt, if n number of coils produce n multiply d phi over dt. So that is magnetic flux. And how is it useful? Basically in generators to create the voltage and electricity. And then we have another thing that we call excitation magnetic field intensity, magnetic field intensity, the excitation H. So just now we have B, now we have H, and the permeability. Okay, so for motor, generator, and transformer, what you need to know is that we don't usually just have a coil. In order to intensify the magnetic field, we put inside the coil a certain material that we call core material. So what is core material? Core material is a ferromagnetic material that conduct magnetic flux better than space or air. So this core material have a properties that we call a permeability. Just now we have permeability of space mu 0. Now every material have a permeability. So here basically an example. I'm sorry again. You may refer to the slide that I give you in the Google Classroom. We have the values. So these are the permeability of usual materials, common materials. So vacuum is very, very low. If you go to copper, it's also low because copper doesn't conduct magnetic field. But if you go, for example, to aluminium and carbon steel and iron basically have a very, very high permeability. It means that it will conduct and concentrate your magnetic field, basically contributing to higher flux, right? If you concentrate magnetic field, what does it mean? It means that you have more field line per surface area, so you have more flux. More flux may generate, therefore, in consequence, a higher torque for motors. So this core material have a permeability mu, and this permeability of we may also refer to relative permeability when we compare the permeability of material in comparison to the permeability of space. the higher the mu, then the higher the magnetic field will be in the core. So if the core is made of iron, for example, you have a better, a lot more magnetic field, means a higher flux inside your core material. If you look at the outside, you have the field line are gapped. So it means that the flux is less, because flux is amount of magnetic field per area. And the relation between the now we have a certain relation between the excitation current. So remember just now, if we have excitation current inside on the coil, we have a magnetic field, and then that magnetic field, there are magnetic field in air, and then there are magnetic field conducted in core. So magnetic field that is excited by the coils is what we call excitation magnetic field. We call it H. And how do we calculate H? H is basically the number of coil multiplied by current divided by the length considered across which we want to calculate the magnetic field, Ni over L. So Ni alone is what we call MMF. MMF, what is it? MMF is basically a magnetomotive force. Magnetomotive force means is the force that creates the flux of magnetic, that creates magnetic field. So if you have current and more number of coils, means you have more magnetic field. So that's why we call magnetomotive force, MMF. H describe the excitation magnetic field, Ni over L. And the relation between B and H is basically B equals to mu H, right? B equals to mu H. Mu is the permeability of the material. So you multiply with H, you have the magnetic field inside the core. H is the magnetic field excitation by the coil. B is the magnetic field that is concentrated in the core. And of course, relation again with flux. Magnetic field is basically flux density, is the flux divided by surface area. So we can see here the flux is more intense compared to the outside. And then so here we have so here we have after defining all those terms like a magnetic field, magnetic force, flux, flux density, or magnetic flux, magnetic field as flux density, and MMF, magnetomotive force, and magnetic field excitation H, and mu, the permeability of material. We can now start to be introduced to magnetic circuit. So what magnetic circuit is, basically it is analogous to electrical circuit. The difference is only that instead of having electrical current inside a conductor, now we have a magnetic flux inside the core material. And instead of having a current source, a voltage source to push the charges, now we have a magnetomotive force that's created by N multiplied by I that create the flux circulating inside the core material. So MMF, what is it? It is analogous to EMF, or voltages, is proportional to the current and number of coils. The unit is in ampere turn. H is the magnetic field excitation intensity measured per length of the core. So imagine if we have a toroid like this and we coil it around it like this. The magnetic field excitation H is basically equals to ampere turn and I divided by the length in which we are going to quantify the magnetic field excitation. And B is the magnetic field inside the core, which is proportional to the excitation H, but by a factor of its permeability mu, right? And then flux, what is flux? Flux is basically the magnetic field density, magnetic field density across the core A. So flux is basically B over A. So these are all the equations that describe the relation between all these electromagnetic parameters. And that's all for this week. We will discuss more about it in the tutorial later. Here we have several quick questions that you may try on your own. You may look at the slide inside the Google Classroom. It is a formative kind of formative quiz that will allow you to check your understanding on the subject presented today. So for example, which of the following statement correct that compares points C and D inside a magnetic field created by this permanent magnet? So you may answer it. There is an answer already. So there's another question related to magnetic flux for both surface. If they are equals, which one have a higher magnetic flux? So there are calculations of comparison you may refer to. And then of course here there is a magnetic flux and Faraday's law application. So a movement of any conducting material inside the magnetic flux will create a certain voltage generated. So for different form of coil and different form of magnetic field variation, you will have different voltages created. You may try it out on your own. And here there is the application of magnetic flux, Faraday-Lenz law. If you have a conductor carrying a current, basically this question asks you what is the value of magnetic flux inside the surface area that is placed next to the conductors. So there is the correction as well. I hope you try it out, and we may discuss more during the tutorial session. So for section 2 is going to be Friday, and for section 1 is going to be Friday, and for section 2 is going to be on Thursdays, if I'm not mistaken. So thank you very much. See you again in the next lecture video next week. Thank you. Bye.